Okay, we will begin in a few minutes. So today we will continue to discuss our study on tensors. And in particular, we're going to take a little bit of a pause on the index notation, at least temporarily, and discuss the modern formalism of tensors. We will do so in a few minutes. We're just waiting for people to hop into the stream. I'll just take this opportunity to answer some of my Discord messages. Interesting. I see there are 8 people watching on my phone, but there's no viewers on my OBS studio. Hi, DMC. So, okay, I think that's enough people. So let's get started. Before we begin, I would like to read this little piece of writing by Peter McCulloch. Peter McCulloch I think he's still alive. I'm not sure. He did phenomenal work in statistics. So, in case you might have heard of this thing in statistics called the generalized linear model. Hi, Vernon. Generalized linear model includes models such as the logistic regression, Poisson regression, and so on. It's a framework that encapsulates the ordinary linear regression, logistic regression, Poisson regression, and more. Okay, among many of his achievements. So, Peter McCulloch also has this book called Tensor Methods in Statistics. You can search it up. It also has a Dover edition, so it's very affordable. And it's a very well-known book in the field of statistics. I think it has over 1,000 citations or something. And tensors are, relatively speaking, in my opinion, less utilized tools in statistics. I mean, of course, we all know tensors are massively important in physics and engineering, in particular mechanical engineering. But tensors are really a powerful tool in statistics as well. Well, we are about to study information geometry. So, and tensors played a huge role in differential geometry. So there's really no surprise there. But there are other things in which tensors can be helpful. In particular, some of the classical methods, such as analysis of variance, ANOVA, is perhaps best expressed in terms of tensor product spaces, something I don't think is particularly well known. And in this book, in particular, Peter McCulloch uses tensor as a calculation tool. In particular, the theory of cumulant, generalized cumulant, more cumulant, Edgeworth theory. So Edgeworth theory is a tool in asymptotic statistics. You can think of this as the extension of the central limit theorem. So that's pretty cool, and tensor plays a role here. Saddle point approximation also has to do with tensors. So again, this is asymptotic statistics. Some calculation with likelihood functions. Very cool stuff in general. But that's not the main purpose of this video. We're going to read the starting paragraphs of the preface. In matters of aesthetics and mathematical notation, no one loves an index. According to one school of thought, indices are the pawns of an arcane and archaic notation. The frontline troops, the cannon foders, first to perish in the confrontation of an inner product. Only their shadows persist, like the putty, I don't know what that is, like the putty of a Renaissance painting are the cherubim of an earlier era, like medieval. I don't even know what this is, but anyway, indices are mere embellishments, unnecessary appendages that adorn an otherwise bare mathematical symbol. Okay, just big A, big T, right? There's no I, J, K, and all that stuff. Tensor analysis, it is claimed, despite all evidence to the contrary, has nothing to do with indices, quote unquote, coordinate-free methods and operator calculus are but two of the rallying slogans for mathematicians of this persuasion. Computation, on the other hand, is a reactionary and subversive word, stripped of its appendages, free from its coordinate shackles. A plain, unadorned letter is the very modern of a model of a modern mathematical operator. Right. So, of course, this is a satirical piece of writing, right? And then you have the second paragraph. Yet this extreme scorn and derision for indices is not universal. It can be argued, for example, that a plain, unadorned letter conceals more than it reveals. A more enlightened opinion shared by the author is that for many purposes it is the symbol itself, that plain, unadorned letter, not the indices, that is the superfluous appendage. Okay, so and here it says, in the matter of index notation and tensor analysis, there are few neutral observers. And I noticed that in past chat and also comments of the tensor analysis live stream, that people who argued, oh, this is too old, like you should, and etc. We'll comment on that later, but this is what the author has to say. Earlier workers prefer index notation partly, perhaps, out of an understandable concern for computation. Many modern workers prefer coordinate-free notation in order to foster geometrical insight. The above parodies convey part of the flavor and passion of the argument that raged for and against the use of indices. So, just as a matter of fact, in this book by Makulak, strongly recommended, by the way, uses the index notation. So as you can see from the first, actually the first chapter is called the index notation, and everything uses the index notation. Okay, so very much in the same definition that we've been using throughout our stream. So there's that. But today we're going to do something that reconciles the two notations. So we've been seeing tensors, like this is our yesterday's notes, for example, as system of numbers, system of arrays of numbers that follow certain transformation law. For example, this is the so-called contravariant vector. And then we have defined the covariant vector. And then we gave the general definition of a tensor, which is something of a monstrosity that looks like this. Okay, which raises a few questions, because if you come from, say, abstract linear algebra, you would probably define. I mean, you would define vectors as elements of a vector space. So how does this definition of a vector, doesn't matter, it's covariant or contravariant vector, relate to the definition of linear algebra? Right? Are they different things? Are physicists and mathematicians talking about different objects? No, not really. So our first goal today, that's why we're going to put a little bit of a pause on the index notation, at least for the first half of the stream. We're going to spend some time trying to reconcile the two languages. And we're going to show that what you learned in traditional linear algebra, the definition of vector actually implies the law of transformation. So what you learned is still safe. Okay, so there's that. And we will gain a better insight of the axioms of the vector spaces along the way. So let's get into today's topic. So first of all, I'm just saying that I'm following a text it's called Linear Algebra by Shilov. Okay, It's a linear algebra by Shilov. So it's an older text on linear algebra, perhaps not the best one if you are completely new to the subject, but I mean, we're discussing tensor analysis on this live stream, so it's unlikely that you are totally new to linear algebra. So linear algebra by Shilov is a great book, and we're following a particular section of it to reconcile the physicist's definition. So to arrive at the physicist's definition for say contravariant vector, contravariant covariant vector. So we're gonna do that. So in particular, we pretty much follows chapter, which is a chapter 5. Okay, chapter 5, coordinate transformation. Coordinate transformation. Okay. Okay. So first, let's give ourselves a vector space. Okay. Let V be an n-dimensional vector space. Let's just call it for the without much loss of generality. Let's just call it the n-dimensional real vector space. And it's got two bases. Okay, I assume everyone is comfortable with working with abstract vector spaces, bases, that sort of thing. Okay. So you got two bases. Basis E consists of E1. Just call it basis E is E1, E2, all the way to En. And you got the second basis, which is called F. Okay, so you have F1, F2, all the way to Fn. Same number of vectors, of course. And now you can expand, say, the new basis. Let's say this is old basis, all right? This is a new basis. You can expand the new basis vectors in the old basis. Of course, you can do that. And you will get a bunch of coefficient. Shilov is a standard on many bookshelves. I don't know, like certainly, I think it's worth mention more. I mean, in the standard internet discussion on linear algebra textbook recommendation is usually Strang and Axler. I do that a lot myself. I sometimes hesitant to recommend this one, but really the book by Shilov has a special place in my heart. I struggle to recommend it because the language might be a little bit antiquated, but the thing is, the math is still very, very solid, and it's timeless, and it covers things that are hard to find in modern linear algebra texts, things like jet, which is a notion in differential geometry. But really, you can explain it using linear algebra. So anyway, coming back to two bases. Okay, so you have basis E and basis F. So we're saying you can expand new vectors in the old bases. Expand Fi. Okay, expand Fi in terms of the original basis. In terms of E1, E2, all the way to En. And by doing so, we'll use the summation notation we've been using so far, right, to save us some writing. So Fi, okay, Fi, let's write it as P Ji, actually Pi, think about that. So, well, you should, let's say this is Fi and then Ej. J needs to be summed over, okay? J needs to be summed over, so Pji, exactly. That's correct. So here in this summation, in this equation, J is the repeated index, so that's summed over. Okay, and I is the free index. Actually, you know what? Let's use alpha. P alpha I E alpha. The summation notation is used. Okay. Alpha summed over. So it's just the basics expansion so far. And of course, this defines an n by n matrix. Because basics expansions are unique. Right? So this is an n by n matrix that's well defined. For any two bases, you can do this expansion. All right. So now, of course, this matrix is also invertible. Mirsky is another Shilov type dopable. Actually, I don't know that one. So yeah, it is invertible. So let's do that as well. So here you can, a second. Let's write. How can I get E from? How can I get E from? You need the inverse transformation, right? The inverse basis. So let's call that. Let's give it a name called Q, shall we? Let's use Q. So E I equals F alpha, and then Q alpha I. Okay. This is the inverse matrix. And of course, the inverse matrix relation can be expressed in terms of Kronecker delta. So this way, so together, the two equations tells us the relation between P and Q. So Fi is P alpha I times E alpha. Well, E alpha is, let's replace I to alpha, and then you need to change alpha in the second equation to something else. Let's say this is Q alpha beta. Q beta alpha. Let's say Qj, okay, Qj alpha, and then Fj. Right. So here in this equation, of course, there are two summations: alpha sum over alpha and sum over j. But since Fi is just the Kronecker delta Ji Fj, together you get the relationship between PQ and delta, which is P alpha I Q alpha Qj alpha equals delta Ji. Okay, that's cool. All right, so we have the relationship between the change of coordinate matrix, the change of basis matrix. Right, this is a change of basis matrix from old to new. If you want to change the, so to say, if you want to change the old basis to the new basis, you use P. If you want to change the new basis to the old basis, you use Q. So this should be clear. Okay, so there's that. And now let's consider coordinates of vector. coordinates of vectors in big V. So what do we mean by that? Of course, it's just a basic expansion. We already did that for the basis vector. We can do that for any vector. So let little v in big V. Then let v in big V, you can expand v relative to E, you can do that relative to F. So V as a basic expansion, this reads, say, you have EI here, and so I needs to be summed over. Let's say the coefficients are xi I. V is II EI, and V is also eta j Fj. So you have two expansions, right? So now we are interested in how the two coordinates are related. So that's the question here. So, I mean, you can consider using the expression for the basis vector. Let's see how that's done. So, the first equation says xi I v equals xi I EI. Well, what's EI? EI is just Q alpha I F alpha. Q alpha I F alpha. And compare this with the last equation. And then you can, in the last equation, you can change the summation index j to alpha, because that's the dummy index. It doesn't change anything. So eta alpha fj, eta alpha f alpha, sorry. And because of the expansion relative to the basis f is unique, comparing the coefficient, we see that xi I q alpha I is eta alpha. So what does this say? Let's rewrite this, okay? So this says that the new coordinates, remember, eta are the new coordinates. This is the old coordinates times this matrix Q alpha I. This is new coordinate, and this is old coordinate. All right? And they're related by this Q matrix. Okay. And let's write it as a matrix multiplication form. So you have eta 1, so alpha is free, okay? Eta 1 all the way to eta n. Actually, before we do that, okay, before we even do that, let's first take a look at the matrix Q alpha I. So that would be Q1 1 all the way to QNN. Oh, not QNN, but Q1N. Yeah, you can do that for 2D. Yeah, I just want to practice summation notation a bit more, if that makes sense. So, I think Eigenkreis's video, if you guys go to Eigenkreis's video, the multiple examples are done in 2D and with actual numbers. But here, since I already covered the index notation, I want to practice this as much as possible. Okay, and QN1 all the way to QNN. Let's see what index is being summed over. Here, I is the second index. That's the index being summed over. So the column index are being summed over. Therefore, we wanted to multiply the matrix. Yes. So here we're doing the contravariant case. We're moving to linear functionals, aka one form. in a second. Okay, so there's that. Here you have this matrix, and then you have xi1 all the way to xin. Okay, and then on the left you have eta 1 all the way to eta n. So that's the matrix form. You see, this forces vectors xi to be column, simply because of how matrix multiplication is defined. Hold on a second, I should use superscript, okay? Just to be consistent, I should use superscript. Because we need to, what we need to do is to sum over the column index, you see, of Q. So by how matrix multiplication is defined, you need to write multiply a vector. So the coordinate vectors are considered column vectors. Yeah, you're feeling tensors already. Thank you very much, Leo. Thanks again for the live stream. So I will. Did I already posted a little post in my community? Yeah, I will do so shortly. So just to remind us what we did today, and go check out your channel. So yeah, that's the law, the transformation law, in index form and in matrix form. Once again, this should be covered in standard linear algebra. Right? And in fact, in linear algebra, choosing an appropriate basis so that the coordinate representation becomes easy is a major theme. Now think about that. You have the eigenvalue decomposition. Eigenvalue decomposition is all about choosing a basis smartly. Right? And often you need to convert the coordinates between eigenbasis and just standard basis, or just any other basis for that matter. Right? And eigen expansion turns out to be not quite able to handle all the cases, so you move on and you discuss things like the Jordan form. And in certain situations, the matrix has a particularly nice eigenbasis. And you have an orthonormal eigenbasis. So all those good stuff. So this is absolutely fundamental. You can already see this is the transformation law of the contravariant tensor. Let's take a look at yesterday's first crucial formula. So you have a bar coordinate. That's the new coordinate. Actually, you know what? This is not right. The contravariant transformation law is here. You see, here we're dealing with curvilinear coordinates in general. So instead of a constant matrix, you have the Jacobian. But the law is the same. Contravariant vector transform this way. Okay, so let's write that down. Compare with what we have yesterday. This is the contravariant transformation law. And it follows from just basic expansion. I mean, we derived the contravariant transformation law of the using an example, right? The tangent vector of a space curve. And the machinery we used was the chain rule from calculus. Here we just use plain linear algebra. There's no calculus going on here. Right? This is the contravariant transformation law. Okay, let's write that down again. So the contravariant transformation law says A bar alpha, say A bar alpha equals AI dx bar alpha over dxi. Same business. All right, and now we can consider the other situation. We're not considering the vector v anymore. Instead, we're considering the so-called dual space. Okay? To recall definition, a dual space is the set of linear functionals defined over V. Okay, so let's write that. So now let's consider the other situation where you have the dual space. Okay. Not every introduction to linear algebra covers dual space, but basically dual space V star is the set of linear functionals. The linear functionals are functions on V that takes a real value, and it's also linear. So phi is from V to big R. So the set of all such linear functionals is called the dual space. Of course, here we're still dealing with finite dimensional vector spaces. Okay, for infinite dimensional vector spaces, there are other requirements for the dual space. Okay, so this is just a set of linear functionals. And of course, this is also a vector space. It is a fact from linear algebra that given two vector spaces as domain and codomains, the set of linear transformation between them is also in itself a vector space. Here, V is a vector space, R is a vector space. Right? So V star is a vector space. So V star is a vector space, and V star has its own, you can do all the usual linear algebra there. Okay, and it's a fact that V star also has dimension n. Okay, I'm not going to prove this, but that's not the focus here. Okay, it's a fact that V star also has dimension n, has dimension of V. So that's why really you can V star and V are isomorphic. So you say, oh, they're isomorphic, so essentially there's nothing new going on, right? The two spaces are isomorphic. No, actually they are isomorphic, but V star is still worth studying on its own because there's no canonical choice to build the isomorphism between V and V star, except perhaps in the case where V is an inner product space. Now here we're not even assuming V is an inner product space. Right? So that's the dual space. And now for the dual space, you can also do the same business we have earlier. So for the dual space basis, you have two bases for the dual space. For V star. Okay, and why don't we give them some names? What would be a good name for the bases in a dual space? Huh? I'm trying to think of a name for the dual space. So let's say, for example, say L, little L. Little L, these are linear functionals. Okay, so little L1 all the way to little Ln. These are linear functionals. Yeah, reciprocal basis you can define. I mean, you can use the E and define reciprocal basis based on that. Yeah, you can do that. Perhaps that's a good idea. Actually. Thank you very much for mentioning that. The dual basis. Right. The dual basis has this property. Dual basis. For V star. Say, what would be the good notation for the dual basis? Hold on a second. Actually, you know what, guys? Let's check out this reference here. This is actually I showcased the other day that This is a good resource if you're interested in multilinear algebra and real analysis for multivariables. Okay, so go check out MIT OpenCourseWare Analysis 2. It's taught by Professor Victor Guillemin. Apologies if I'm mispronouncing his name, but this is a gold mine for rigorous multivariable calculus, including vector calculus. Okay, the textbooks are Spivak's Calculus on Manifolds as well as Moncrief's Analysis on Manifold. So in particular, there is a particular nice set of supplementary notes which I open here on multilinear algebra. So go to MIT OCW Analysis 2, Reading, and Notes on Multilinear Algebra. Multilinear algebra is the modern name for tensor analysis or tensor algebra. Okay, so that's the modern terminology. But if you go there, you can see, yeah, that's the dual space, right? That's the dual space. So the dual space is a set of linear functionals, as mentioned. V star is a vector space. It's called the dual space. Suppose you have E1 all the way to En as a basis for V. And then you can define E star, right? E star, yeah, E star, that's a notation for inner sum. Now I see the left general relativity and right quantum mechanics. I'm a physicist. Yes, so you see that they're both physics, right? And in different areas of physics, different formalisms of tensors dominate. So in general relativity, you will see a lot of what we've seen earlier, right, in our previous stream, things like this, bunch of indices. Whereas in quantum mechanics, you see a lot of old times, right? So they really are the same thing. But here, let's take a look at the notation here. If we use the E star as the dual basis, okay, let's use the E star as dual basis. The E star, the dual basis, has this property. It evaluates, hold on a second, it evaluates the standard basis to be the Kronecker delta. So let's use that notation. Dual basis, I'm going to actually use E star I this way. E star I, this is a linear functional. It takes Ej to Kronecker delta Ij. So together, E star 1, okay, E star 2, all the way to E star n forms a basis for V star. Okay, and of course you can prove this is indeed a basis and do all those things. The details are in the notes. Okay, in this notes, you can actually check this is actually a basis. You see here, claims this is a basis, but I'm not going to do it here. So perhaps we will save a dedicated study of modern multilinear algebra for a different stream. Okay, as I mentioned yesterday, as applied mathematician, being bilingual or even trilingual is part of the work. The ability to translate results between notations, because we are the people who does scientific communication as applied mathematicians. Right? Truths can come in different languages. Okay, of course you can have your preferred language just like anybody else in the world, but as an applied practitioner, it's important to be able to communicate with different fields. Okay, but I mean it's kind of fun, isn't it? It's like learning English and Chinese, and you translate between them. You see the subtleties and advantage, disadvantage between them. That's pretty cool, in my opinion. Okay, so yeah, so this is a dual basis. This is a dual basis. So I was thinking, if let's say if you expand a general linear functional in that basis, what would be the coordinate? What would be the coordinate? And how is that related to the new dual basis? This is old dual basis. So the dual basis works like this. So given the vector space V without the star, you can define the dual space V star, and V can be assigned a basis, so EI. And given EI, you can get the other dual basis. So that's the dual basis E star. E star works for E star is the basis for V star. Okay, that's the logic here. Because I understand that dual basis is perhaps dual space, dual basis, etc. is not part of. Sometimes it's not part of the standard linear algebra course. Okay, not every course teaches that. So that's why I'm spending a little bit more time on this subtlety, because the dual space coordinates transform differently. The dual space coordinates transform differently than compared to the coordinates in V. This is where the difference between covariant and contravariant comes from. So here we have the contravariant transformation law, and then we're going to here we're actually in the process of deriving the covariant transformation law. Covariant transformation law are the components is satisfied by the components of elements in V star, so-called covectors. Chat says for an identity basis, it is the identity. Exactly. So here, if you have, you mean the standard basis, right? I'm not sure what you mean by identity basis. I assume this is, you mean the standard basis, because if you're in Rn, the standard basis put together forms the identity matrix. So here you have the dual basis. The second dual base, f star I of fj works the same way. It's the same definition. Okay, this is the definition of the dual basis. So dual basis eats. Okay, dual bases are elements of V star. Elements of V star eats vectors and spit out real numbers. This is what they do. Okay, and dual basis eats the given basis. If the index match, then it's 1. Otherwise, it's 0. This is how it works. So now you have f star 1, f star 2, all the way to f star, oh, not j, but n. My bad. This is the other dual basis. So now let's consider the same functional, but in two bases, right? Now let's, much like what we did earlier. So you have the two bases, and now you consider an arbitrary vector v in big V. And now let's consider an arbitrary phi in V star. So phi is a linear combination of E star i's and F star I. So let's write that as, okay, so phi equals, say, E star I. What notation should I use? Let's just say C, okay? Because here earlier we used Greek letters for the components of vectors in V. Here let's just use Latin letters for components. Latin letters for components of phi. Okay, Ci E star I. Okay, that's the first expansion. The second expansion reads dj, say dj f star j. We need to figure out how do they transform, huh? We need to figure out how do E star I and F star j transform. Okay, what's the relationship between them? That's the idea. What's cool about Reed's representation of linear cooperative linear functional? Well, that's in functional analysis. It's inner product spaces. Inner product space. Because here we're just dealing with a general finite dimensional linear space or vector space without additional structure. So let's think about how do E star I transform. So E star, what does say? E star, hold on, let's say F star J. Well, how does F star J relate to all the E stars? Okay, so the dual basis transforms this way. So let me think about it. Well, starting from this identity, F star J of Fj, oh no, F star I Fj equals Kronecker delta Ij. And what is Fj? Well, Fj is, we have an expression for that, right? You can use the change of basis vector, the change of basis matrix, P alpha I. Let's put that down. So we need that. So we wish to substitute that here. So this will give us F star I of P alpha J E alpha. This is Fj. And because F star I is linear, you can pull out P alpha J. So it's P alpha J F star I of E alpha. Hi. So Y, C, D have index at the bottom on vectors. So you see, I did something sneaky here. Because the index for the dual basis are upstairs. Why? The dual basis works this way. The dual basis, when evaluated at the basis E, so the dual basis E star I, when evaluated at the basis Ej, is the Kronecker delta, up and down. All right, and here, because of E star I is upstairs, the expansion coefficient Ci is downstairs. And I'm not writing this as random because I'm trying to derive the covariant transformation law. Take a look at what we have yesterday. The components of covariant vectors are all downstairs. This is yesterday's definition. And we motivated this definition using by considering the gradient vector of a scalar field. So you see, here, yesterday we did this example. Suppose phi is a functional point, right? And the point is a geometric object. It has nothing to do with coordinate system, but it can be represented using a coordinate of n numbers, x1 all the way to xn. For the moment, if you consider this as the Cartesian coordinate, taking the partial derivative here, taking the partial derivative gives you the gradient vector, this one, d phi over dxi. That's the gradient vector. And now let's consider coordinate transformation. Xi to yi. Y is a function of x1 all the way to xn. So this, you can think of this as a polar coordinate. Right. And then just by chain rule, d phi over dyi and d phi over dxi, or in this case d phi over dx alpha, is related by this expression. And motivated by this, we call that the covariant vector. The difference between covariant vector and the contravariant vector is that the Jacobian are different. So to transform the components of a covariant vector, you use the inverse Jacobian. Okay, I wrote d old over d new. See, x alpha is an old coordinate, x bar is a new coordinate. So d old versus d new. And earlier in the covariant vector component, it transforms according to the forward Jacobian, d new over d old. So therefore, they make them different kinds of objects. So here we formalize this distinction by defining the dual space. Right? The dual space are set of linear functional. It takes elements in V and returns a real number. So the index notation is consistent with what we did yesterday. Okay, so now it's just a matter of deriving the relation between Ci and dj, which I'm still trying to figure out. Okay, so what is the relation between the dual basis vectors? Okay, so here. Can we perhaps what do we need? Well, we need f star I e alpha. Need f star I e alpha. So this needs to be expressed in terms of ei star, because otherwise you can't express that. Actually, you know what? You can. You can write e alpha in terms of f. Right? This is what you can do. Right? So here we use the expression for f. And also you have e alpha. What is e alpha? E in terms of f is here. Bunch of q's. This is ei in terms of f alpha. So let's substitute that as well. So get p alpha j f star I of e alpha. E alpha is, let's swap I to beta. So you get q beta downstairs. Actually, no, you can't do that. I mean, I want e alpha, so here, so q downstairs use alpha, sure, but upstairs needs to be changed to say k. Okay, q k alpha, q k up, alpha down, and fk. And then use linearity again. This becomes p alpha j, q k alpha, f star I of fk. And now you can use the dual basis definition. This is exactly the Kronecker delta. So hold on a second. Did I get a tautology? This isn't good. Let's just finish writing this. And now because of the Kronecker delta, you swap all the k's to I. So you get p alpha j q I alpha, which is already something that we have earlier. Oh, so this is not a particularly enlightening derivation. So what I wanted is as follows. Actually, you know what? Actually, this is messed up. This is messed up. I want the relationship between Ci and dj. On this relationship between Ci and dj. So why don't we take a vector, huh? Why don't we take a vector? Say, because this is actually, never mind. So let's consider the following. So consider phi of ej, phi of ej. So consider phi of ej. So phi of ej would be, I want the transformation law between, law of transformation between Ci and dj. This is what we want, okay? So let's consider phi of ej. This way you just get Ci e star I of ej. And this is exactly Ci. By definition, this is delta ij. So it's Cj downstairs. This is Cj. On the other hand, use the second expression. Well, what's that? Well, you get phi of Ej is dj f star j of, no, that's not good. That's not good at all because the indices mess up. Okay, so let me rewrite this as d, say alpha. D alpha, that's the dummy index, d alpha f star alpha of Ej. We can do that, no problem. And now use the basic expansion. The original basic expansion. So d alpha of f star alpha, and then Ej is now, well, you have to change that to q alpha downstairs, let's say beta upstairs, okay, f beta, all right? And now by linearity, I would say you can already see how this is going. So this is d alpha, q beta alpha is taken out, and then you have f star alpha of f beta. Okay, but this is just the Kronecker delta alpha beta. Replace the index, and you get d alpha. Wait. There should be a free index. There should be a, oh, I'm stupid. Here it should be j. Ej. Okay, it should be j. Here. I don't know why. Yeah, this should be j. Okay, so now it looks okay, because otherwise there are two summation. If I use alpha down here as a two summation, it makes no sense. So it's q alpha j. This is q alpha j. So now let's see. Compare the two results. Therefore, you get Cj. Now you get the transformation law. Cj equals d alpha q alpha j. Okay, so this is good, and this part is unnecessary. This is a tautology. This is unneeded. Okay, so that's how we get the transformation law between the component of one form. Okay, this is also, sorry, one form, linear functional, same thing. Ci and dj are the component of phi, expanded relative to the dual basis. And this is what we have. Let's think about what this means in a matrix form. First, let's write down the matrix Q. So get Q11 all the way to Q1n. Going down, you get Qn1 all the way to Qnn. Which index is summed over? Well, the row index is summed over. If the row index is summed over, then if you want to cast that into a matrix multiplication, you need to sum over each column, right? You sum along each column. So you have to left multiply, because that's just how matrix multiplication is defined. So because this way you need d1 ... all the way to dn, and this is, of course, gives you another row vector c1 ... all the way to cn. So you can see why there's this distinction between row vectors and column vectors at all, because they represent different objects. Row vectors are coordinate representations of objects in V star, whereas column vectors are coordinate representations of objects in V. And what is that? This is the law of the covariant transformation. Let's take a look at what we have yesterday. I was just talking about the gradient. inspired by the transformation law of gradient, you get a bar I, okay, lower index equals a alpha, once again lower index, of dx alpha over dxi. That's d old over d new. Okay, d old coordinate over d new coordinate. Let's write that down. So there you go. So this is the covariant transformation law. This is the covariant transformation law. They're saying a bar I equals a alpha Actually, here do we use alpha? Actually, we use alpha as free earlier, so let's use that same convention. A alpha equals ai. Okay, and now this is dx over dx bar, old over new, I upstairs, alpha downstairs. The point is, this is the inverse of, you're using the inverse of P. Before, we used the, hold on a second. This is not right. Something is messed up. F is P. Alpha. Hold on a second. This should be the inverse. Why am I using Q? Here, in the first relation, eta is the old, eta is new, right? Eta is new. Actually, oh, sorry. This is still correct, but no. I think what I wanted is to write dj. The d is the new coordinates, right? That's why. Okay. So in the previous transformation law, left-hand side is the new coordinate, right-hand side is the old coordinate, right? But here I messed that up. C is the old, D is the new. See, C is the old, D is new. Okay, so that's I think we can just rewrite this. Okay, let's rewrite this. So instead of considering, okay, let me erase all of that. Okay, sorry about that. So, okay, get rid of everything here. Even though this is still correct, but it does not conform to the form that we wanted, right? So let's redo it. That's okay. So let's consider phi of fi. Okay, phi of fi. So phi of fi, on one hand, is phi of fi is dj f star j of fi, and that's a Kronecker delta ji. Swap the index, you get di. That's it. Okay, on the other hand, phi of fi, use the first expression, you get ci e star I. Oh, I cannot use I in a dummy index, so let's use alpha. Alpha here, okay? E star alpha evaluated at fi. Once again, use the basic expansion. the basic expansion, there should be here P. C alpha times E star alpha, P alpha I E alpha. Actually, alpha is used again, that's not good, so let's use beta here. Beta inside the bracket, okay? Change that. Okay, and now use linearity, pull out the coefficient. You get C alpha P beta I, C star E star alpha of E beta. And this is, of course, Kronecker delta, delta alpha beta. Replace the index, and you get C alpha P alpha I. That's good. E star and F star are basis covectors for different coordinates. So they're just actually we're using the same coordinate. Remember here we're defining basis vectors first. So starting with V, you have two bases. Okay. If you have V, once V is given, V star is fixed. The space V star is fixed. Once E is defined, E star is defined. So I'm not introducing a brand new arbitrary basis for V star. Does that make sense? There are only two free choices here, okay? So for a given vector space V, the old and the new basis EF can be arbitrarily chosen. But once you have done that, V star, the space, and the dual basis, plural, E star and F star are both determined by these relations. So these aren't arbitrarily chosen. Okay, so here, we just redid the derivation, this time expressing D in terms of C. So therefore, you got DI equals C alpha P alpha I. The point is, here you're using the inverse of the previous matrix. And you're considering D and C as row vectors instead of columns. So D1, okay, Dn equals C1 all the way to Cn. Okay, P11 all the way to P1n, go down, N1 all the way to Pnn. Okay, so the key is there are two operations. So the two observations. D is considered a row vector. C is considered a row vector. Right, and the P matrix is inverse of Q. Just like in yesterday, we used the forward Jacobian for the contravariant transformation law, and the covariant transformation. In the covariant transformation law, we use the backward Jacobian. All right, so that's the vector situation. So we didn't, in yesterday's discussion, we didn't really introduce vector in a new way. In fact, yesterday's transformation law, the two contravariant and covariant transformation law are implied by the abstract definition of vector space and dual vector space. Hello, mom. I'm not your mom. Okay, but hello, yeah. So that's the gist of it. So you're not really inventing new math here. Okay, so but what about tensors? Well, we've been discussing vectors. What's the tensor then? Okay, so let's get to the nodes. So here, we get to the nodes here. So in this node, we also define tensor. So tensor is what? Okay, so imagine you have a v-dimensional vector space, and you make a k copies of v. And T takes an object takes an element in vk to R. Vk is the set of all k tuples. Okay, this is a collection of vectors. The collection of vectors. What did we see earlier has this format? Well, for a start, dot product has this format. Let's say, for example, if you have k equals 2, then dot product takes two vectors and returns a number. So that's an example of such T. And also determinant. So let's say let V equals Rn and k equals n. It takes n vectors and returns a number. If you treat the determinant as a collection of column vectors, okay, the v1 is the first column all the way to vn is the last column, and so on. This function is said to be linear in its ith variable if we fix all the other variables. Okay, you fix everything except vi, and that turns out to be a function that is linear in its ith argument. So this is called linear in its ith argument. Okay? Controlling the variables. You're controlling everything else to be constant. If it's linear in its ith variable, well, it's just said it's linear in its ith variable. Okay. If T is linear in all of its arguments, it's called K-linear. Right? K-linear or multilinear, hence the name of the subject of multilinear algebra. A multilinear function in general is not linear. Right? It's not linear, and the elements are called K-tensor. So this is a tensor. So simply by linearity, you can define tensors. And just like in vector spaces, we can define vectors. We can define vector spaces axiomatically. Right? You can define how addition works, how scalar multiplication works, and all of that implies vector spaces have basis expansion. And from basis expansion, we derive these transformation laws of the coordinates. And here we can define a tensor, okay, as a quote-unquote unadorned, unembellished single letter, just T. And then you can assign basis to V. You can assign basis to V, and you can see how do the coordinates of T changes according to the change of basis, basically. Okay, so why don't we just do that? Why don't we just do it? Let's just take k equals 2 as an example, okay? Just to save some writing. K equals 2. V is still n-dimensional vector space, as we did earlier. And now let's say T is bilinear. Say T is bilinear. What happens? So now let's consider T. T maps from V times V to R is bilinear, like a dot product. So first, we need an index description, actually a coordinate description of T. How do you describe T coordinate in coordinates? K-linear is more about emphasizing the ring K, not necessarily. So that's a big K. So here in this set of nodes, we're not doing any sort of abstract setting. Here it's a real vector space. Okay, K is not a general field. Because this set of nodes is geared towards real analysis, okay, so we're dealing with real vector space. Is this a real vector space? Actually, I found a full book version of the lecture notes for analysis 2. It's called differential forms. It actually includes much more things than differential form, but yeah, this is basically chapter 1. The notes here, this set of notes is the chapter 1. So let's take a look at the book version. Perhaps that's a bit more clear, because here it just says it's a vector space. It didn't say it's a vector space over what, right? The scalar does not really matter here. I think it's real. Yeah, it should be real, because if you use a general field, say big K, you use big K as the scalar, then the linear functional should map from V to big K. Here we all assume a finite dimensional real vector space, as I did there. Okay. All right. So I know, like from an abstract algebra perspective, right? Abstract algebra perspective, you should use a general field, but it's of very little concern to us. Okay. Okay. So I apologize for the lack of generality. Okay. So here, the main goal here is to hammer the intuition, right? We're not being super formal here. Okay. I think this is enough generality already. So if T is bilinear, if you have two vectors, say V and U in big V, we wish to express the value of TUV. Once again, using index notation, summation notation. So let's do the same basic expansion business. Expand. So V is, say V, do we have a nice letter? I really don't know, man. Because Greek letters are also used as indices, so I have to be careful here. Okay, so why don't we just use A? Okay, so I ran out of ideas. So A times E, A upstairs I times E I downstairs. Okay, this is what I mean. So expand V relative to the first basis E. The same E, okay? Still hasn't changed. You now just introduce this new object called a bilinear function or bilinear form. Same V, same basis, same two bases, E and F. We just wanted to understand how do components of T transform. We're not being super formal here. Look up from writing tensor basis index expansion notation. Well, there's a degree of formality, right? If you go to, let's say, and proper treatment of tensors from an abstract algebra perspective, this is still very concrete. Right? If you, in an abstract algebra setting, you would define you don't use vector space, instead you use module. As far as I'm aware, I don't pretend to be an expert, but this is already pretty concrete. A little bit more abstract than what we did yesterday, okay? But still pretty concrete. So this is V, and also you can write that as, say, B, BF, oh no, BJ, FJ, right? Two expansions. So if you use the first expansion, let's express TUV. So what is TUV? So TUV is T of U, which is, oh no, I need an expansion for U as well. What am I doing? So this is, you know what, let's just call this TVU, okay, TVU. TVU. Okay, U is, say, CI upstairs, EI downstairs equals DJ upstairs, FJ downstairs. All right, so TUV in the basis E, okay? Then basis E you get AI, EI, and CI, EI. That's not good. Let's use C. Huh. That's confusing. That's confusing. So I'm not a great index chooser. Modules are when you generalize beyond fields. I see. But that's just that's too much generality. Okay. So we wanted to keep things focused on the main intuition. So screw it. Let's just use CJ. Okay. CJ, EJ. Okay. Fine. and then expand. Use bilinearity to expand. You just get AI Cj. You can take out those two coefficients and get T of EI EJ. T of EI EJ. And similarly, this is also T of BI FI DJ EJ. Right? And you get BI DJ T of EI EJ. All right? They should be the same. Oh, actually, sorry. My bad. How come I'm so careless? This should be F. F downstairs. F downstairs. Okay? So they should be the same. It should be the same. And we're just going to define, okay, T of EIEJ as, let's gonna write this as AICJ, and this is, let's call that T, because I's are downstairs, you see, IJs are downstairs, let's just say TIJ downstairs with no other embellishment. Okay, so now the second would be, because F is, remember, that's the new basis, right? So to indicate that's new, let's use the bar. BIDJ, and then you have T bar IJ. IJ. So the question is, how do TIJ and T bar IJ relate? That's the question here. So, of course, so let's first write down the equation. BIDJ T bar IJ equals AICJ TIJ lower downstairs. Okay, downstairs. So I want to express the new expression, okay, the new components in terms of the old components. So that's why we do this. We wish to get rid of the BIDJ. But how do we do that? How do we do that? Let's think about the relationship between AB and CD. Think about that. Remember, A and C. A is the old coordinate, C is the new coordinate. So they are related. According to our transformation law earlier, here, how do coordinates transform? To get the new coordinates of a vector, you use the old coordinates of a vector and then times the Q matrix. So let's do that. So this means the new coordinate Ci, okay, the new coordinate Ci is the old coordinate A. Let's first not write the index and then multiply by Q. Multiply by Q. All right, so this is A. This is A. So the index of A should be summed over. So let's use A alpha, shall we? A alpha, and upstairs index should survive, and downstairs index is summed over. Okay, so this is Ci, and dj and bj are related in the same way. So let's write dj is b beta qj beta downstairs. This was the coordinate transformation law for vectors in V that we derived earlier. So let's hold on a second. Hold on a second. Actually, guys, you know what? My goal is to get rid of the B and D. B and how do I get rid of the B and D? So B is related. Hang on a second. Yeah, AC are related and BD are related. That's right. So how do I get rid of the B and D on each side, huh? Okay, so let's try for B. For B, let's still feels a little bit weird. Actually, this is nonsense. This is complete nonsense. Sorry, my bad. A and B should be related. Okay, A and my God, A is the coordinate for V. C is the coordinate for U. They don't know each other. Like, I was silly. So yeah, B, the coordinates BJ should be in terms of AJ. So sorry, let's redo this. Okay, let's completely redo this. So the application of the formula was wrong. So still you use the Q matrix. You use the Q matrix, and now B, the new coordinate for V, is related to A, and the new coordinate for U, which is D, is related to the old coordinate C. Now this makes more sense. Okay, this now makes more, because I was trying to substitute and it obviously looks wrong. So BJ is a alpha QJ alpha. Okay, that's nice. And DJ, oh, actually, you know what? Here, because of BI, I'm going to use I. Use I, okay? So BI is A alpha QI alpha, and DJ is C beta, okay? C beta and QJ beta. Cool, awesome. And now we can substitute. Now we can substitute. So the left-hand side now becomes, left-hand side, you see, BI is just A alpha, and then Q I alpha, that's BI. DJ is C beta, QJ beta, T bar ij equals AIC, AICJ, TIJ. All right, so let's take a look at what is going on here. So on the left, what are the free indices? Well, on the left, on both left and right, IJs are the free indices. IJs are, but here you have alpha and beta. You have alpha and beta. So you want to swap alpha and beta. You want to swap alpha and beta to be, okay, so let me regroup this. Okay, so let me regroup this. You just get A alpha C beta QI alpha QJ beta and T bar IJ. Wait, hold on a second. This isn't right. IJ, yeah, IJ is summed over. IJ is, actually, there's no free index on each side. There's no free index on each side. Okay, this is fine. This is fine. What I want is, I want the index for alpha and beta to match. I want the alpha and beta to match. I want alpha to be alpha, but here is you get I, perhaps multiply that by a Kronecker delta, I guess. Does that help? Cj Tij. I want the relation between, I want Tij bar, okay, I want T bar in terms of M bar. I feel like we're getting close. Maybe we can try multiply P. Let's multiply, say, recall the relationship between P and Q. So P, say P here, I want to get rid of the, so I want to cook up a Kronecker delta. What's the relationship between the P and Q? I derived this earlier. Yeah, here. Yeah. This should be helpful for for index swapping. ING a dummy index, so you can change it to alpha and beta. Yeah, so I know these are dummy index. That's true. So so let's swap that. So A alpha C beta to be Q. I want to swap I to something else. Say K. QK alpha QL beta T bar KL. Okay, so nothing has changed. AICJ TJ TIJ. All right, and then I'm going to pair the left hand side with multiply both sides by P. So here A alpha C beta times P, which one needs to be summed over? Say, I want to change this because I want an index to match. So some index has to, because if you change to something else, it still doesn't matter that these two contract, no? Because I want P and Q to contract. I want P and Q to contract. Actually, guys, let's take a look at the portion of the book on scalar product of two vectors. Okay, it's a very short portion. It's a very short portion, which we skipped yesterday. Actually, perhaps it was not a good idea to skip that. So let's we'll come back to this. Okay, I'm pretty sure we're getting close. It's just I'm still not very comfortable with index notation. So this is part of the book by which we used yesterday by Harry Lass on the scalar product. So the scalar product is a special case of a bilinear form. See, scalar product is a special case of a bilinear form, and I think the transformation law should be the same. So let's read this and see if we can get some inspiration. So you get AI upstairs. So there's one up and one down, huh? That's one up and one down. Okay, sure. I mean, not exactly the same idea, but hopefully we can figure out the strategy. So you have AI upstairs and BI downstairs. And then, of course, A alpha, B alpha is just the one number, right? So now, what is the form? It says, what is the form of It says, what is the form of A alpha B alpha if we make a coordinate transformation? Okay, so AI upstairs is covariant, so you have this transformation law. D, hold on, this is, oh, this is the opposite. Here, so here you actually write, because in the definition we've been using, you always write the new one on the left. Here is actually the new one is on the right. So I was confused. Oh, why do you use the backward Jacobian or the inverse Jacobian? This is because you change the order. Okay, but either way, now the old A alpha is the new A beta times the inverse Jacobian. This is the same as the contravariant transformation law. Remember, A bar alpha is A beta beta upstairs, the forward Jacobian, dx beta over dx bar beta over dx alpha. And now you have the if you move A bar alpha to the right, then this is the correct form. This is a contravariant, and B bar alpha is what? I don't know why it somehow randomly changes order. It doesn't change anything mathematically. It's just harder to read. But B bar alpha is, oh, actually it should be downstairs. B bar alpha downstairs is B beta. Right. And then you use the backward Jacobian, D old over D new. Here, beta should be downstairs. Is it right? Yeah, beta should be upstairs because here B has a downstairs beta. Dx alpha. Okay, dx bar alpha. So those are the two, and then you do the dot product. You multiply the two. Yeah, multiply the two, and you get a Kronecker delta here, which shows the same. So the scalar transformation doesn't change. The scalar is a scalar. It's simply the coordinate is invariant. The coordinate is invariant. It's not quite the same as we did earlier, right? It's not quite the same. So I'm just a little bit confused here. Actually, you know what? This is what I don't like. I'm not a huge fan of this at all. So let me delete that. Because I forgot one thing. Okay, I forgot one thing. So we will not even use this. Don't even use this. So here, at this step, I wanted. What did I want? Okay, so I wanted T bar. Okay, so I wanted define this. Perhaps the approach was sort of messed up. Define T bar ij to be the outcome of T of Fi Fj. Define that, all right? And Tij to be the linear function, the bilinear form, T of Ei Ej. Okay, needs a transformation law. So let's use just the original coordinate, not the coordinate, but the basis transformation. What is Fi? Recall, this is F in terms of E. This is more direct, huh? Yeah, I think this is more direct. This is actually much easier than I previously attempted. So this is f alpha, fi. Fi is just p alpha. There you go. P alpha I E alpha. Okay, what's fj? Same business. Let's write p beta j, p beta j e beta. All right, let's pull everything out, and you're done. So just p alpha I p beta j, and then what? And then t e alpha e beta. Just use bilinearity. Okay, there's no need for this nonsense. Okay, there's no need for this. Okay, much easier. Just this. So guess what? This is just hold on a second. Yeah, this is p alpha I, p beta j, and then t alpha beta. Boom, you're done. That's the transformation law. So is this covariant or contravariant? What sort of tensor is this? Well, you see what it uses? It uses the P matrix. And what thing uses the P matrix? Contravariant. Oh, sorry, covariant. Actually, yeah, covariant. Okay, is that a good idea, huh? Is that actually a good idea? Yeah, that is a good idea. That is a good idea. That is a good idea. So what I'm saying is this is a this is it uses downstairs. This is a covariant second order tensor. And does it conform to our definition yesterday? Let's take a look. Okay, so yesterday we have the definition of a general tensor at the very end. This is a monstrosity, right? Beta index, downstairs index is, say downstairs index here is this object here. This is a covariant of S, order S. This is a covariant. So that's it. So therefore, a bilinear form, right? A bilinear form. Therefore, a bilinear form is a covariant vector of order 2. Is a second order, a pure covariant tensor. Right? Just from bilinearity. See, just from the definition of tensor as a bilinear form. Here, all the k's are the same, right? If you mix, say, k and k star, if you mix, sorry, all the v's are well, the original v, right? If you mix up, say, v and v star, you get tensors of mixed type. Okay, let's see an example for that. Let's suppose if you say, let's say if you consider t, which is from v times v star to r. This is bilinear. So it takes a vector and a linear form, a linear functional, and returns a real. Say this is bilinear. This is bilinear. So the same business, okay, so you have the same business. So let's say you have, how do we do that? do we define, say, first of all, what should be upstairs, what should be downstairs? Actually, you know what? Let's consider the coordinate formula. So what should the coordinate form look like? So the coordinate formula for t. What's the coordinate formula for t? Let's consider mixed type. Coordinate formula. So pick a still you're using the E basis for V and E star for V star. So little v is in big V. Little v is say AI EI. Okay, and pick a phi in V star. And phi is what? Because now you have to use E star I. The coefficient is downstairs, say, why don't we just call that BI, huh? Or use J. Okay, summation convention. All right, so what should the coordinate look like? So let's say this is T V phi. It takes a vector and a covector and returns a real. What does that do? Well, it is T of AI EI BJ E star J. Taking out the coefficient, you get AI upstairs, BJ downstairs, T of EI and E star J. And we're going to define this, okay, and we're going to define this to be Tij. Okay, I downstairs, J upstairs. This is Tij. And similarly, we define T of T bar Ji, J upstairs, I downstairs, as T evaluated at the new basis, which is F I downstairs and F star J upstairs. Can we derive the transformation law between T bar Ji and Tji? Okay, just follow the same method above. All right, so by definition, transformation law. So it's not mysterious at all how the definition of tensor in both setting, okay, in math and in physics, or in modern or classical, whatever you want to call it. There's no mystery here. So by definition, Fi is what? What is Fi? Fi is the formula, we have that earlier. Fi is P alpha. That's right, P alpha I E alpha. E alpha downstairs. What is F star J? What is F star J? Well, F star J, we also have that earlier, right? F star J. Did we derive that? What is F star J as in terms of E star J? Do we have that expression? Let's maybe go back and derive that. Okay, so I feel like I haven't derived it. Okay, let's just do that on the side. What is F star J? What is F star J evaluated EI? That's easy. That's right? Sorry, I want F star J in terms of E star J. I want F star J in terms of E star J. I want this to be in terms of E star J. So how do I do that? How do you write the new dual basis in terms of the old? Well, these two are related, right? These two are related. So we have the transformation law between C and D, so that should be useful. That should be useful. These two are the same, and C and D are related. So okay, here, let's put it here. All right. So dj f star j is ci star I. Actually, actually, we can pick a special. We can pick a special phi. And pick a special phi. That would be helpful. Phi, this is arbitrary. Phi, this is an arbitrary phi. Hold on a second. Where were we? Yeah, this is an arbitrary phi. If I pick, say, if I pick, okay, if I pick phi just to be f star j. Here, if I pick let phi just be f star j, then what happened? Then, well, f star j equals cij, which is what I wanted. Okay, cij is what I wanted, and then times e star I. This should equal Kronecker delta j ji f star I, right? Just swap of index. Just swapping index. So I want C. I want CJI. What is CJI? Because that's what where I'm struggling with. So I wanted the, because if you have f star j in terms of e stars, then we're done. Right? Just use multilinearity after that. But here, what's that? Let phi to be f star j, then you do this business of, okay, let's see if Shilov can help me out here. How do transformation of linear form works? It says, okay, let L be a linear form defined on a space. Does the coefficient of a linear form transform? No, I don't want the coefficient of linear. I want the basis of the linear form. So how do you transform from f? This is an interesting question on its own, right? How do these two transform? We've been dealing with transformation of coordinate, but how do the vectors transform? F star. Well, one way to brute force this is you can think of f star j as completely defined by its action, right? By its action on the basis E. Right. The thing is, right? So f of ej, it's the f of ei. Let's consider f star of j. Let's feed that with EI. Let's just do that. Let's consider that. Okay, so what is EI? We have the transformation formula earlier. EI is Q alpha I F alpha. Use Q matrix. Use Q F. So Q should have an I downstairs, alpha upstairs. Yeah, Q alpha I F alpha. And this is what? This is Q alpha I F star J F alpha. And that's the Kronecker delta. So this is Q alpha I. This is Q alpha I Kronecker delta J alpha. J alpha. But Kronecker delta can be written as, you use a trick. So Kronecker delta, delta Ji can be written as E star J acting on EI. E alpha here. Right? I just wanted to write this as something acting on EI. If that's done, then F star J is determined. But here, instead of EI, you get an E alpha, and alpha needs to be summed over. So it's not quite that. It's not quite that. All right. Okay. I'm gonna AI. Okay. So here, I'm gonna AI a little bit. So ChatGPT, help me out. How do dual bases transform? Nice. Okay. How do dual bases transform? It says it's the opposite of the transformation law for the basis itself. Okay. So let V be an n-dimensional vector space with these two bases. That's the transformation. And then you define, okay, epsilon, that's the dual basis. Okay, determine B, right? Exactly. We want the new dual basis to be in terms of the old new dual basis. Old dual basis, right? That's the idea. We want that. Impose defining property, okay? Impose defining property. Yeah, this is Kronecker delta. I start from the delta. Okay, I didn't use that. So that was the issue. So yeah, you would probably expect the inverse matrix to pop up somehow, but we wasn't quite able to derive it. Okay, so let me rewrite it. Okay, so here. We want the relation. Okay, so you want to have F star I to be some coefficient C. I'll add the indices later, but acting on E E star j, E star j. So j downstairs, I upstairs. So you want Cij so that this is true. So you want that. Okay, and then use the defining property. Delta ij equals f star I acting on fj. Acting on fj. All right. So substitute our expression. So you want C ij E star j. That's your f star, and then express fj. Fj uses the P matrix. Yeah, Fj uses a P matrix, so P alpha E alpha J. Can I use J? No, I can't. No, I can't. Yeah, I have to use J here because J is free. I can't use J here. That's the issue. So yeah, perhaps it's when you write expression, it's first important to notice which one are free, which one isn't. So here, because J is free, so I have to use something else. Let's say beta. Okay, so that's cool. And then use by linearity, actually just linearity. Ci beta P alpha j is E star beta E alpha. All right. Okay, so this is Kronecker delta, delta beta alpha. Swap the index, you get C I beta, Ci beta P, Ci beta P beta, yeah, P beta J, P beta J. And because we have the inverse relation between P and Q, this forces C to be Q. Right? So this just says C is the inverse matrix of P, which is just Q. This is Qi beta. This is Qi beta. So Ci beta is Qi beta. And therefore, F star I, you now have C. F star I is, J is the dummy here, so you just write Qi beta E star J. So that's how the dual basis transform. So that's how dual basis transform, and then now substitute that here. F star J is done, everything is done. So you just use Q. Okay, so what's F star J? F star J, as mentioned, F star, this is F star I. Okay, F star I is Q. So you need Q. Okay, anyway, Q, E. So Q, J should be on top. J is free. E star beta, and the Q has a beta subscript as well. So this is how the dual basis transform. And now take out the coefficient, and you're done. So P alpha I, Q J beta, T E alpha E star beta. And this is, of course, just T alpha downstairs, beta upstairs. So that's the transformation law, and this gives you the mixed tensor transformation law. So there's no mystery here. Mathematician's definition of tensor implies the physicist's definition of tensor. Okay, T unprimed coordinate P alpha I, Q, J beta. This is mixed tensor. This is second order mixed tensor. Mixed tensor 1, 1. 1, comma 1. All right? So hopefully now there shouldn't be any doubt between well, the thumbnail, right? You guys seen the thumbnail, the same thing. Although there's one thing that needs to be explained. That's the tensor product symbol, because we never defined that, right? What's about the tensor product symbol? Okay, because right now we haven't even introduced tensor product even in the index form. But basically, you can think of building tensor from vectors. Building tensor from vectors. So this is Sheldon Axler's linear algebra done right. And in the very last chapter, actually, the very last section, is called multilinear algebra and determinant. We all know Axler hates determinant, right? So he saved determinant till the very end. And after determinant, he introduced the tensor product. So Chad earlier said, oh, this is how tensors were introduced in quantum mechanics. Indeed. Based on my limited knowledge, this is how quantum entanglement is described using tensor product spaces. Okay, so at this point, it is perhaps unnecessary to get into such content, because our goal, remember, is still to understand curvature. Our goals in this series is rather limited. We just wish to understand curvature and be comfortable with working with indices, that sort of thing, and gain some geometric intuition. We will look at this stuff when it is called for. Okay, it's just my way of working. Okay, I tend to set a concrete goal. And center everything around that. Okay, it's just a time management thing. So I'm going to skip this for now. Okay, but at this point, there shouldn't be any doubt between the definition of tensors as this monster and the definition of tensor as multilinear form. Okay, so the two, perhaps the multilinear form version is more succinct. Right? It implies the transformation law. That's why perhaps mathematicians like it. Right? But there's absolutely nothing wrong with this definition of tensor. Okay, and it can get you very far. Okay? Truth can come in different forms, and we don't discriminate based on how it is expressed, what kind of language it is expressed. And in fact, for applied mathematician, a large part of our work is to translate notation. Right? So you wanted to express the intuition and observations of applied scientists to the pure math community. Perhaps new branches of mathematics can be developed from there, and also introduce the precision, right, and generality of pure math into applied fields. So it's a two-way street, and I really enjoy this process, and I hope you guys enjoy too. All right, so at this point, let's continue with the classical tensor stuff. Okay, so we're going to live with this, the monstrosity I just mentioned. Okay, so we're going to live with that. So yesterday, even though we saw the tensor definition, there was still something that seems a little bit mysterious, because in all of our examples, there is no such factor of dx over dx bar raised to the n. Okay, so here it says when n equals 0, namely there's no such factor, the Jacobian factor. If there's no such factor, we say the tensor field is absolute, quote unquote absolute. So far we've been dealing with absolute tensor field. Otherwise, the tensor field is relative to weight n. A tensor density occurs for n equals 1. Okay, so because these notions are undefined at this stage, I can only imagine this will play a role somewhere down the line. If not, we are just going to deal with absolute tensors, and I think that will give us let us go very far as well. Okay, so far, even though this looks a little bit mysterious, we shouldn't be too bothered by it, and the terminologies now should make sense. All right. One thing I guess is perhaps worth noteworthy. So we introduced these two transformation laws yesterday by considering two kinds of geometric objects. When we introduced the contravariant transformation law, we consider the space curve in n-dimensional space. Right? Consider the space curve in n-dimensional space, and then consider the tangent vector and how tangent vector transforms. And it turns out tangent vector transforms according to the contravariant law. Right? So that's the origin story of the contravariant vector. Think about how many inputs and how many outputs are involved. In a space curve, you have one input. You just have one input. That's the parameter t. And you have n output, right? xi equals xi of t. I equals 1 to all the way to n. So you have n output, one input. Is Rn valued function of one real variable. And in that case, that leads you to a contravariant vector of order n. Actually, order 1 with in n dimension. So contravariant, purely contravariant. Okay, so purely contravariant tensors or purely contravariant vectors seem to take value in an n-dimensional space. And its argument is just 1. It's just a scalar. It takes values in n-dimensional space. On the other hand, the other geometric object from which we introduced the transformation law for the covariant vectors is a scalar field. In a scalar field situation, it takes n numbers as input and just returns one output. So it seems like the covariant vector returns a scalar, right, as opposed to the previous situation. In a space curve scenario, you output n numbers and eat one number. Here in the scalar field, you eat n numbers and returns one number. That makes sense? So the contravariant index corresponds to the output. That's what I'm trying to get to. The contravariant index corresponds to the output, whereas the covariant index corresponds to the input. Of course, in both cases, you have so-called vectors, right? Contravariant vector versus covariant vectors. Because the output or the input is just one number, there's no need to introduce a second index. Here, for example, in covariant vector, there's only one output, just one number, so there's no need to index that. In the contravariant vector case, there's only one input, so there's no need to index that. Right? So there's no need to index that. So you see, this is another way to associate the term contravariant and covariant. Okay? Just an interesting observation, in my opinion. All right, so let's continue our discussion on tensor. Let's copy the definition of tensor and do more examples. Okay. So we're getting closer to geometric invariant, I believe. So this is a definition of tensor. Chat has been real quiet. Is everything still make sense? Okay. So we spend this amount of time. Okay, I gave 4 examples, right? How do vector components transform? How do the components of linear functionals transform? Okay, how do components of a bilinear form transform? So let me just label these examples. So this is 1. This leads to the transformation law for the contravariant vectors. 2, dual basis leads to the transformation law of covariant vectors. 3, bilinear form. Bilinear form leads to the transformation law of purely covariant tensor. And finally, 4, if your input of t is a mixture of t and t star, that gives you a mixed tensor transformation law. Okay, so I hope this settles the confusion between the physicist tensor and the mathematician's tensor once and for all. Okay, and there's no scientifically speaking, there's no priority or hierarchy between them. Okay, and which one you use is simply a matter of objective and taste. All right. So here, let's consider the following a new discussion. Okay, is that two tensors are said to be of the same kind if tensors have the same number of covariant indices and the same number of contravariant indices and are of the same weight. Okay, so this shouldn't be surprising. So it proves that, okay, it proves that this, then it says tensor of the same kind. Let me just put that down. Okay, here. Because there's a lot of writing. I'm just going to paste it here. It's a lot of writing, all right? So as we said, the upper indices are contravariant indices and the lower indices are the covariant indices. Okay, and the proposition says the sum of two tensors of the same kind is a tensor of this kind, right? And the proof is rather obvious, even though writing that is painful because of this formula. There's so many indices. Basically, let's prove that. Proof. The sum of two tensors of the same kind is a tensor of this kind. So d bar a and so on to b, c and so on to d. Okay, so let's say this transform according to 450, 490, 495. All right, so you get dx over dx bar, determinant to the n. Okay, t alpha all the way to beta, bunch of indices, sigma all the way to tau. You know, I was going to say that one of my struggle when I first studied it like 10 years ago was the difficulty of coming up with meaningful indices. Okay, I was just sitting there and thinking, okay, what letter should I use? Which ones are already used? Okay, and it actually takes extra time. Dx tau over d. Hold on a second. Sorry, this is not alpha. My bad. Okay. So d x should be sigma. My bad. Summation sigma. So you got sigma. So you got the how many of them? Yeah, sigma to tau downstairs, and then this is finally dx bar to d. Yeah, to c to d conforms to the free indices here, and also dx bar a, you need dx bar a all the way upstairs to dx bar b. Okay, and then what? You have to contract all these alpha all the way to beta, so dx alpha all the way to dx beta. So that's one tensor, okay? This is one tensor, that's t. And then you have another tensor, so just to save myself some writing, you simply just change big T to another letter, say S. Of course, from a mathematician point of view, the same proposition means if you have two multilinear functions, T and S, the sum is still a multilinear function, which is obviously true. Okay, and then you add them together. Well, you let's call that U, then U bar A all the way to B, C all the way to D, okay, is defined as T bar A all the way to B, C all the way to D, and then plus S bar A all the way to B, C all the way to D. All right. This is of course just U alpha all the way to beta, sigma all the way to tau, and the same business. Okay, and the same business. Okay. All these Jacobian here. All right. So, that's the first proposition. The second proposition says the product of two tensors is a tensor. The products of two tensors is a tensor. And we show that through a special case, it says. Okay. Which is enough to illustrate the general idea, proposition. The product of two tensors is a tensor. Just as a side note, tomorrow there won't be any live stream at all. So today there's going to be one in the evening to make up for that. Typically, we on Sunday we do mathematical statistics as well as ballistics. So this way, this is not canceled. Okay, we still do that, but it's just going to be tonight. I know the schedule is a little bit crazy nowadays, but well, I'm on vacation. I might as well just do more math. The product of two tensors is a tensor. Okay, so this is a special case. It's enough to showcase the general situation. Let's prove to a special case. So let's consider T is a mixed type. Okay, so the T bar AB is dx over dx bar absolute value squared. I thought initially that it was just the power of 1, but turns out you can have higher power. I don't know what is it for actually. I have no idea, but I suspect it has something to do with integration, but I might be wrong. Okay, so the weight factor currently is unclear. Sorry guys. I wanted to, but just to be clear, okay? The product of two tensors is a tensor. It doesn't have to be the same kind. Doesn't have to be. I just need to feed my cat real quick. Give me a minute or so. I'm back. All right. Thanks for sticking around. All right. So just want to mention the difference between the two propositions. Okay. In the first proposition, the two tensors has to be the same kind. Whereas in the second, it doesn't matter. It doesn't matter. So it's like in vector or linear algebra, you have to have two vectors living in the same vector space to do addition. How do you define the product of tensor? Yes, I'm just going to write that down. So here, good question. So you just literally do element-wise product. This is element-wise product. Actually, you know what? That's not element-wise product. This is if you. I mean, I'm gonna use a vector as an example. I'm gonna use a vector as an example. So what do you mean by a product of two tensor? So let's say if you have a vector, say a1, a2, a3. Say you want to multiply that with another tensor. Say we call it b11, b12, b21, b22. Actually, you know what? This is perhaps a bad idea. I should use upper indices here. Column vectors has upper indices now. Column vector now use upper indices. Okay. Of course, this matrix multiplication would make no sense here. So we use a different symbol, this dreaded old time symbol. Channel is new gem. Thank you so much. Yeah. So if you just use this old time symbol, and what you get is something called a Kronecker product. This is what you get. Okay. So the size is now what? So the size is like this. So you can think of, there are different ways to think about this. So basically, let me just, you can think of the first vector, just a vector times b11. So you get a1, b11, you get a2, actually a2, b11 as well. Yeah, a3, b11. Okay, and a1, b12, a2, b12, yeah, and a3, b12. Okay, and then you have this crazy situation, which is a3, a1, sorry, a1, b21, a2, b21, and a3, b21. There's that. You already know what the rest should be. Or know what the rest should be. Okay. So there you go. A1, b22, a2, b22, a3, b22. This is what it looks like. Okay, think in terms of block matrix. But of course, the matrix representation is limited because in general, tensors can have many indices, right? So this is just element-wise. Actually, it's not even element-wise because element-wise needs a matching size. This is a Kronecker product. In matrix, in linear algebra, this is called a Kronecker product. So here, let me just give you this special case, which I haven't finished writing. So T is a tensor. So and here T is of mixed type, so it has two indices, one up, one down. Okay, and let's write down the transformation law. Hold on, a on top, yes, a on top, and dx alpha at the bottom, right? So now, okay, so that's T. You can think of T as a 2D array. And then you have S. S is a 1D array. S is a 1D array. So S bar I, okay, S bar I transforms according to x dx over dx bar determinant cubed. Okay, this is just an example. For example, there's no special reason of choosing this, but the way we multiply the two should be clear for all types of tensors. As sigma dx bar I over dx sigma. So that's the two tensor that we were trying to multiply. And the multiplication is trivial. So you literally just multiply both sides, like how you multiply real numbers. So tensor multiplication is no different from just regular multiplication of numbers. Okay, so it's like here, what I did here, you see, AI multiply BKL is just literally that. There's no, okay, that's just the multiplication. Okay, you can't even write equals to something because it would be literally the same as this one. The idea is the result of the multiplication is still a tensor. Okay, let's multiply the two, and you get T bar AB S bar I. This as a whole, that's a new tensor. So that's a tensor of order 3. Okay, which is contravariant of order 2 and covariant of order 1. Okay, so and you get dx over dx bar determinant to the power of 5 T alpha beta as sigma, same object, and then you have the Jacobian on the right, so it's dx beta, okay, dx beta over dx bar b. That's the inverse Jacobian. That's the corresponds to the contravariant index. Then you have two forward Jacobian, dx bar a over dx alpha dx bar I, sorry, dx bar I, another forward Jacobian, dx bar I over dx sigma. So that's it. Right. So yeah, in linear algebra, this is called a Kronecker product, but really it's a special case of tensor product. Okay, it's how, like, the dot product is a special case of inner product. Of course, in the modern, quote-unquote, modern treatment, you do this axiomatically. In quote-unquote modern treatment, you do, like the MIT OCW analysis 2, you do everything axiomatically. So instead of giving a formula for the tensor product, you just specify what kind of property you want it to have. What does the old-time symbol property does it needs to have, right? So here we actually give a formula for the Kronecker product. All right, so these are the two quote-unquote obvious properties. Okay. Anyway, just to the weight, you see you can see the type and the weight are different. The type and weight of S and T are different. It doesn't matter. The result of the multiplication is still a tensor. I remember somebody once said, also a guy on YouTube, I think the channel is called Visual Math. Right? So he does a lot of abstract algebra and geometry, that sort of thing. Okay, so let me just find that channel for you guys. which I also quite like. So I think he said something along the line of tensor product is something that everything you want a product to behave, okay, it is true. Well, except perhaps commutativity, but everything else behaves the way that you want it. Distributivity, associativity, all those nice things. So basically, that's it's called visual math. That's the channel. Yeah, he does a lot of abstract algebra and geometry, that kind of thing, and also it's a Lie theory. Pretty cool. Okay, representation theory. I think a lot of people on my Discord want to learn something about representation theory, so go ahead and follow him. Very nice channel. And if you look at, for example, a playlist or courses, perhaps what is linear algebra, and go ahead and check out his explanation of for example, trace. I remember this video in particular. It's such a nice video. It was an eye-opening experience. I remember he gave a characterization of trace, which I never seen before. Yeah, and yeah, tensor product. This video is here. It's super popular. See, a lot of people are interested in tensor and stuff. You see, 25K views. Perhaps it's because this concept is surrounded by some sort of mystery. Hopefully what we did today demystified a little bit, right? Because in physics and modern algebra or geometry text, they're defined in some drastically different looking terms, one with indices, one with no index at all. So it might be hard for beginners to decode this. But anyway, let's continue. So you have these operations, right? Sum and product. These are operations of tensor. So you can do sum, you can do product, and now we are introducing a third kind of operation called contraction. Contraction. So let's see. Once again, this is just an example, and you can apply the same principle even for tensors of not exactly the same kind, but that's okay. So let's see, you have a tensor of this form, okay, contraction. So this is so-called the absolute tensor without weight. A bar ijk, okay, mixed type, equals A alpha beta gamma, and then dx beta over dx bar j, okay, dx gamma over dx bar k, and then finally the upper index, the contravariant index, so dx is gamma, all right, dx alpha, no, not alpha, but dxi over dx alpha. This way you get ijk at the end, okay? And alpha, beta, gamma are summed over. So that's the so-called, that's an absolute tensor. If we say replace k by i, replace k by i. Replace k by I, well, on the left-hand side, now you have the situation of repeated index I. One up, one down. So by the summation convention, this implies a summation. So how does that behave? Right? So now you have to sum over I. Well, let's just do the substitution first. So on the right, you get A alpha beta gamma, partial derivative dx beta over dx bar j, dx gamma over dx bar k times dx, actually k is replaced by I, right? So So here I needs to be summed over actually. So here k is changed to I forgot because here I is here. So this is the replacement. All right, and finally the last Jacobian factor is unchanged. But notice what happened. Notice what happened. So here the last two factor is a chain rule. It's just dx is a, hold on a second. Is that a chain rule? Yeah, certainly seemed like it. That's a chain rule, so that's dx gamma over dx alpha. So that's a chain rule. And then now what happens? Remember, here, this is dx gamma over dx alpha. These are the same set of coordinates. They are in this, they're in the, you see, this is old coordinates, this is old coordinates. Remember what we said earlier, this is just the Kronecker delta. This is in the first stream. Of course, that's completely trivial. It's because in any coordinate system, doesn't matter it's old or new, okay? The coordinates themselves are independent. Here, this is something we introduced in the first stream. If x1, x2 all the way to xn are independent variables, then dxi over dxj is just the Kronecker delta. It's dx1 over dx1 is 1, dx1 over dx2 is 0, and so on. This is the Kronecker delta. So here you get a Kronecker delta. Okay, this is a Kronecker, which is just a Kronecker delta, delta gamma alpha. And because you have a delta gamma alpha, then you can do the index change. So it says, look at what things are being summed over. Well, looks like in delta you got gamma and alpha. Right, gamma and alpha. So let's write that. Okay, this is A alpha beta gamma dx beta over dx bar j times delta gamma alpha. All right. So what's going on here? Well, alpha needs to be summed over, right? Alpha needs to be summed over, and when delta equals gamma, okay, when delta, you can consider swapping gamma to be alpha, or you can consider swapping gamma to be alpha and then get rid of the delta. The result is the same. So by swapping index, you just get A alpha beta alpha dx beta over dx bar j. Right? I mean, you can swap alpha. You can say swap alpha to gamma. Then you would get A or A gamma beta gamma. It's the same. It's just gamma and alpha is a dummy index. They mean the same thing. Right. So this process is called index contraction. So you replace one index by another. Okay, so that in a tensor expression you have repeated index. You have repeated index. As we can see, replacing index gives you a new tensor. So this is what it's saying. So the conclusion is, so AI, Ji are components of an absolute contravariant vector. Remember, I is repeated. So really, there is only one free index, just J. See, and this is the law of hold on a second. This is law of what? The transformation of this, yeah, of a covariant. No, this is a covariant. This is a covariant, but why does it say it's contravariant? That's wrong, no? Hold on a second. So basically, but in the text it says, okay, so in the text, what we just did, okay, so I think the textbook might have a mistake, but this is, you see, here, the free index is downstairs, and this is the inverse Jacobian, d old over d new. So aij are the components, ai, ji are the components of absolute contravariant vector. No, this is covariant. Contravariant vector has upper index. Here I is not. I think this is a mistake. By replacing, you see, this is here. This is a mistake. This is new. This is old. And this is d new over d old over d new. And we said earlier here, see, d old over d new is covariant with a downstairs index. So I'm pretty sure the textbook made a mistake here. This is not contravariant, this is covariant. Okay. So here, the textbook has a mistake. Okay, this is the component of a covariant vector because of the transformation law. So the idea is index contraction gives rise to another vector. So think about it. So here, if you replace I and j, replace k by I, only free index is j. So it makes sense that because j is a downstairs index, what remains is a covariant vector. And indeed it is. It's just that in the textbook there is a mistake. Okay? Okay. Wow. So, and it says, in general, we equate a certain covariant index. Yeah, we equate a certain covariant index to a contravariant index. That's called a contraction. So you can't do, say, you can't do two index downstairs to be the same. This isn't allowed. This isn't allowed, okay? So to do contraction, it has to be one up and one down. This is what we call a contraction. I don't know, let me actually highlight it that way. Sum on repeated indices and obtain a new tensor. This is called contraction. Okay, cool. So these are three operations. All right, so the next operation is called the quotient law. So the next quotient, let me write down the quotient law. The quotient law works as follows. Okay, it says assume for the expression, assume the expression AI BJK is a tensor for all contravariant vectors AI. AI. All right, and we will prove that the BJK is a tensor. Prove BJK is a tensor, and of course, according to the index position, this should be a second order covariant tensor. Okay, so this should be a tensor. So I'm gonna finish discussing this example, and we'll close the stream there. And we will 2 hours later at 7 we'll start the mathematical statistics and ballistics. Okay, so how do you prove that it's a tensor? Well, you show that it satisfies the tensor transformation law. Right. So there you go. By the fact that AI BJK is a tensor, you can have the following equation. So AI BJK is a tensor, so it transforms according to AI bar. By the way, this is a product. By the way, this is a product. The product. It's like you can somehow cancels out AJ, right? And the remaining is still tensor. That's why it's called a quotient law. So the new components AI bar B JK bar, okay, is the old A alpha B beta gamma times the transformation law, the Jacobians, all right? So one index upstairs, so that's a contravariant. So it's D new over D old. I'll add the indices later, okay? And then you have two indices downstairs, so 2 inverse Jacobian, D old over D new twice. And now add indices. Indices. So IJK should be the new indices. All right. So here I should be on top, and alpha is under. Yeah, and here beta needs to be sum over. JK needs to be downstairs. Okay, J is here, K is here, beta and gamma are on top. All right, so that's the assumption. That's the assumption. This is the tensor. And now we're going to do something. AI is a contravariant vector. AI is a contravariant vector. So because of AI is a contravariant vector, you can collect, say, A alpha and its corresponding Jacobian. Right? The corresponding Jacobian has alpha in it. So if you put them together, that will just gives you the new component A bar I. That's just A bar I. That's just A bar I, and the rest are unchanged. And because this is true for all AI, the rest must be the same. So that's the end of the proof. Right. Since AI bar is arbitrary, then the two must be the same, and we're done. Right? Of course, this new set of notation takes a lot of practice to master. Okay, so so far we're still just dealing with the index notation and the definition of tensor. Okay, so this is not just pure notation anymore. Okay, actually, new mathematics is being introduced. We're going from linear algebra to multilinear algebra now. Okay, so because our, as I said, immediate goal is to get to the, because our immediate goal is to get to, what's that, the curvature as soon as possible. The curvature Christoffel symbol, and Levi-Civita connection the fundamentals of Riemannian geometry as fast as possible. Okay, we will ignore for the most part. We'll ignore for the most part the modern abstract formulation, because once you are familiar with these operations, those things aren't going to feel like a meaningless abstraction or just rather mysterious objects anymore. It's just a succinct way to repackage something that we're already familiar with at that point, by that point. Okay, so there's that. Okay, so that's it for today's stream. I hope we had a good time. Okay, I certainly did. Because, as I was saying, I think I derived the physicist's definition of tensor from multilinearity almost 10 years ago, and I forget about it. I forget about the detail. I know it could be done, but still, it's nice to revisit it. Okay, it's nice to revisit. So now the definition of tensor should be very clear. We choose to work with the coordinate notation, okay, simply because it lends us immediate computational power, right? Not because we hate abstraction. Okay, and the book that we will take a look at on August 8th stream, Information Geometry, also heavily uses coordinate system. Okay, there we will treat probability distributions as being parameterized by coordinates. So you will be working with coordinates almost all the time. So get used to the index notation, and then the main statistical so to say intuition of information geometry, and then you can learn more geometry for that matter. All right. So thank you very much again for